the sun, a blazing ball of plasma that has dominated our sky for billions of years. But what powers this celestial giant? Deep within the sun's core, under unimaginable pressure and heat, lies the answer: nuclear fusion. Here, in this cosmic crucible, atoms are forced to fuse, releasing the energy that bathes our solar system in light and warmth. The sun's core is a place of extremes, where temperatures reach 15 million degrees Celsius and the pressure is billions of times that on Earth's surface. Under these conditions, matter behaves in extraordinary ways, giving rise to the phenomenon that fuels our star. Unlike chemical reactions we observe on Earth, which involve the rearrangement of electrons, nuclear fusion delves into the heart of the atom. It's a process where the nuclei of atoms, typically hydrogen in the sun's case, are forced together despite their natural repulsion. This fusion process results in the creation of heavier elements, primarily helium, and the release of a tremendous amount of energy. This energy, in the form of high-energy photons, then begins a long journey from the sun's core, eventually reaching us as sunlight. The most common fusion reaction in the sun is the proton-proton chain reaction. It all starts with two protons, the positively charged particles found in the nucleus of a hydrogen atom. These protons, driven by the immense heat and pressure of the sun's core, overcome their electrostatic repulsion and collide at incredible speeds. This collision, however, is just the first step in a multi-stage process. When two protons collide at sufficiently high energies, one of them undergoes a transformation. It converts into a neutron, a neutrally charged particle, through a process known as beta plus decay. This transformation also releases a positron, the antimatter counterpart of an electron, and a neutrino, a nearly massless and chargeless particle. The result of this first step is a nucleus consisting of one proton and one neutron, known as deuterium, a heavy isotope of hydrogen. The newly formed deuterium nucleus is now a target for another free-roaming proton in the sun's core. When this proton collides with the deuterium nucleus, they fuse, overcoming their repulsion due to the immense energies involved. This fusion creates a nucleus with two protons and one neutron, known as helium-3, a light and stable isotope of helium. This step also releases a high-energy gamma-ray photon, a form of electromagnetic radiation. The final step in the proton-proton chain involves two helium-3 nuclei colliding. This collision results in the formation of a stable helium-4 nucleus consisting of two protons and two neutrons, the most common form of helium in the universe. However, this final fusion also releases two protons back into the solar plasma. These two protons are then free to participate in new proton-proton chain reactions, perpetuating the cycle of fusion within the sun's core. Throughout the proton-proton chain reaction, neutrinos are produced as byproducts. These ghostly particles interact very weakly with matter, allowing them to escape the sun's core almost immediately. Neutrinos provide us with a direct glimpse into the heart of our star, carrying information about the fusion reactions taking place millions of kilometers below the sun's surface. Studying these neutrinos helps us confirm our models of solar fusion and provides valuable insights into the fundamental properties of these elusive particles. The sun's energy output is truly mind-boggling. Every second, our star converts approximately 600 million tons of hydrogen into helium through nuclear fusion. This process releases an unimaginable amount of energy equivalent to the detonation of billions of atomic bombs every second. However, only a tiny fraction of this energy actually reaches Earth. Yet this tiny fraction is still enough to power all life on our planet and drive our climate and weather patterns. The sun's energy in the form of sunlight is the foundation of life on Earth. Plants use photosynthesis to convert sunlight into chemical energy, forming the base of the food chain. This energy then flows through ecosystems, sustaining all life forms on our planet. The sun's warmth also plays a crucial role in regulating Earth's temperature, making it habitable for life as we know it. The sun's influence extends far beyond just providing light and warmth. The solar wind, a stream of charged particles constantly flowing from the sun, interacts with Earth's magnetic field, creating the auroras, those spectacular displays of light in the polar regions. Solar flares, sudden bursts of energy from the sun's surface, can disrupt our communication systems and satellites. Understanding the sun's behavior is crucial for protecting our technology and ensuring our continued exploration of space. Scientists have long dreamed of harnessing the power of nuclear fusion here on Earth. Fusion power holds the potential to provide a clean, safe, and nearly limitless source of energy. Unlike nuclear fission, which powers current nuclear power plants and produces radioactive waste, fusion reactions produce very little radioactive waste. Achieving sustained fusion reactions on Earth, however, is a monumental challenge due to the extreme temperatures and pressures required. The Sun, our nearest star, is a magnificent example of the power of nuclear fusion. It is a celestial furnace that has sustained life on Earth for billions of years and will continue to do so for billions more. Understanding the Sun's engine, the intricate dance of nuclear fusion in its core, provides us with insights into the very nature of stars and the universe we inhabit. As we continue to explore the cosmos and unravel its mysteries, the Sun will forever remain a source of wonder and inspiration.